week. And what that means is that throughout the week, if you go to your lab, if you go to your hack, if you go to a help hours, then you'll be able to show your fixed hack or fixed lab, and you'll be able to get those points back if you donked one of them up. Remember that hack 4 is due tonight, and if that's something that you need to redo instead, well, then you have until up till the exam to do that, and you won't get it graded back by then. But of course, if you need to show that to an LA, you can do that as well. There is nothing due this week except for the exam on Friday. So today we're going to continue with the functions and not quite finish up on that. We'll pick it up next week after the exam. But Wednesday, what I'll do is I'll bring in last semester's, or I guess last year's, first exam, and we'll do it. And if we get that done, then we'll take the 2 years ago exam and do that one. We'll do as many exercises as a review as you want on Wednesday. And then, of course, Friday, there's no class, there's no live stream. I will not be here, of course. You can take the exam anywhere you want. It'll open up at 2:30 right now on Canvas. You'll have until 11:59 p.m. to submit it on CodePost. You can submit as many times as you want. All work must be your own, okay? Remember that we do use a system called MOS, measure of software similarity, that is able to detect copying or software that's too similar. So make sure that all work is your own, okay? All right, any questions on how this week will go? No? All right, well then let's pick it up from last time where we were writing our own test cases. And what I want to do is I want to look at that in a little bit more depth. What we were doing is something called unit testing. Now that we've got functions, we have a notion of what a unit is. More generally, a unit is any piece of code, usually a function, but it could be a piece of code that includes like a class or an entire library or a collection of functions. But it's a unit that can be tested. When you unit test it, it's an indivisible piece of code that's treated as one thing, as a black box. So a function, your procedural abstraction, you're looking at this function as a black box that you cannot open up and look at the innards of. If you could do that, then it's not a unit, right? We're gonna treat it as a black box. We're gonna feed stuff in, we're gonna feed it input, and we're going to get output. How it works, I don't know, we don't care, right? We don't want to know, because we wanna blindly test it to see if it's correct. A unit test for that unit, for that function, is an input-output pair that is known to be correct. Now, it's known to be correct by some means other than your code. If you just feed input to your code, and then you look at the output, oh, that must be it. So I'll take that output and say, yeah, it passes. That's not testing, right? That's just trusting your code. I mean, you should have trust in your abilities, but always also verify. You know, the old saying, trust but verify. It's a known input-output pair that's known to be correct by some means, like, say, pulling out a piece of paper and writing down what the input should be and what your expected output should be based on your own calculations. Pulling out your calculator, typing a bunch of stuff up and making sure that it's correct. Wolfram Alpha. Or if you want to get to more sophisticated tools, you can have entire libraries that do nothing but generate mock data for you. We won't get into it that deeply, but there are resources out there that you can use. When you unit test, you do so by feeding that input into the unit, the function, and comparing the result to the known correct output that you already computed through some other means. We call those the actual output and the expected output. If those match, then we say that it passes, right? That unit test passes. If they do not match, it fails, right? Okay? And here is a diagram from my book, not from Zybooks or anything, but there's a diagram about unit testing. And this entire box here is the unit test. All right? Here's our test case, which is an input-output pair that has already been generated that's independent of our code, the unit down here. We take that input and we feed it into the unit. That gives us some output. We've got the expected output, the actual output, And if they're equal, then we say that the entire thing passes. If they're not, then it fails. Now, one unit test is not enough, right? If you've got a unit, a function, then you need at least 2, 3, 4, however many test cases it takes to convince yourself that it's probably correct. Grouping those together gives you what's called a test suite, right? So if I've got multiple unit tests for the same unit, I collect them all together, and now I've got a test suite that can be rerun, right? The advantage of doing this is that it's repeatable, right? If in the future somebody reports a bug, it says this program's not working, right? And well, what do you mean it's not working? Well, here's the input that I give it. Here's the output that I get. Okay, well, why is it not working? Well, I expected this output. Guess what? They just gave you a new unit test, right? A test case that you can put into the unit tests. Not only that, but tests, again, like I said, should be repeatable, right? We want this to be approach this from a scientific point of view, where we run the tests, great, they all pass, right? Oh, now we've got a bug. Somebody's reported that bug. We go back to the drawing board, we fix that bug, right? And we run our tests again to make sure that we didn't break anything. That's called regression testing, right? So suppose that I go and fix this bug for this one failing unit test, or one test case that's failing. It now passes. Great. But the changes that I made go and break 5 other test cases. They were passing before, but now they're all failing, right? I have regressed, right? What it means, generally you want to make progress. You want to make sure that you're passing more and more test cases. But if you're now failing the test cases that you were passing before, you have regressed, the opposite of progression, right? You've regressed. And so unit testing allows us to run regression testing. And I don't have to go back and, set up the tests again, recompute all my input and output expected, stuff like that. All I have to do is hit a button and it takes care of it for me, right? So the more tests that you have, the higher certainty that you have that it's correct, okay? You will never get 100%. No amount of unit testing will give you a 100% guarantee that your code is correct. Right? Only a mathematical proof can do that, and even that has its shortcomings. Right? There's some meta-mathematics that says that there's no such thing as a proof for any algorithm for any input. It can only provide you more and more assurance that your code is correct, and the overall goal here. One goal is to provide 100% code coverage. There we go. So we're never going to have a 100% guarantee that our code is 100% correct, but we can have a guarantee that we have at least one unit test for every single possibility. One example, right? Your tax program from, I think that this was lab 3, right? There were, say, 5 different possibilities for taxes, like 10%, 12%, 22%, or whatever, right? If I had only 2 test cases, at most, I could only test 2 of those possibilities. The other 3, who knows? They were completely untested. I would only have about 40% code coverage. If there are only 5 cases and I'm only testing 2 of them, I've only got 40% of the possibilities. I need at least 5 test cases there in order to cover all 5 possibilities. Not only that, but I probably want 1, 2, 3 for each one of those, 15 test cases instead. That's going to give me more and more code coverage, right? You want a test case for at least, or you want at least 1 test case for each possible computational path, right? So if your tax is within this range, that's 1 computational path. If your tax is in a different range, that's a second computational path, et cetera, et cetera. But you also want to test corner cases, edge cases, error cases, et cetera, right? For example, corner cases. 1 corner case on the tax, for example, would have been, say, I don't know what the tax brackets were, but let's say that it goes up to $19,999, and then the next one is $20,000. I would want to test an edge case, maybe the $19,999, and then also the $20,000 to make sure that both of those work. I would want to test edge cases. What happens when I have zero tax dollars? What happens when I have zero children? Error cases. I ask you, do you have children? Yes. And I say, how many children do you have? You enter -5, right? That's an error condition. I should be testing for that. Is our code robust enough to survive the ID10T user, right? In fact, you can take this and go even further. You can do what's called fuzzing, right? Generate random values in an attempt to break your code, right? So that chaos testing, I forget what. There's a couple of other names for this, but fuzzing is what we call it. We try to break the code, right, by just giving it bad values over and over and over again, right? So again, there are some problems with respect to test cases. Lack of code coverage, right? You're not going to. It's not possible for you to have 100% guarantee that your code is correct, but it is possible to have 100% code coverage. And there are tools out there that can look at all your test cases and look at your code and tell you, oh, you forgot about this one. You need to generate a test case for this. We're not going to get into that. But you could also have problems like false positive. A false positive, right, is when a test case is wrong, but the code is correct. Right? So, for example, I could have written my test cases over here and $10,000 at 5% interest over 5 years. I could have actually had a typo there, $188.72 on accident. Our code was correct, right? Or at least we have high assurance that our code is correct. But my test case here is wrong because I did my calculations wrong, or I pressed the wrong button on my calculator, or when I went to Wolfram Alpha, I had a typo or something like that. Right? That's a false positive, telling us that it would actually fail, but our code is actually correct. So you do have to be careful about that. You also have to be careful about a false negative. Right? Is when when there is a bug in your program, but your test case is do not catch it, right? Catch it. In other words, they both agree, but they are both wrong, right? And this usually happens when you don't write a good test case. When you take your input, you feed it in your program, you get your output, and you go, oh, okay, that must be it. I'll just go ahead and feed that back in as the expected output. Well, of course, that's because you started with an agreement to begin with, but your code is still wrong. Your code is wrong, your test case is wrong, but they agree, so it looks like it passes. Okay? All right, and there's also an internal debate of TDD, right, which is test-driven development, right? You will get advocates that say you should write your tests, all the tests, 100 tests, before you ever even start to write your code. And that's a philosophy of test-driven development. The exact opposite of that would be no testing at all, which is quite common, right? Where we'll just, everything works, looks like it works, we'll just go ahead and go with it. I don't subscribe to either one of those philosophies, right? Because both of those are wrong. There has to be a middle ground in there somewhere. You don't have to write all of your tests up front before you have an idea of how your code should work. Write maybe a few tests, right? To understand the algorithm, to understand how your code maybe you want to write your code. Then go and write your code. Oh, okay. Now a test case is failing. All right, go back and rewrite your code. All right, great. Now everything is passing. Go back and write some additional tests. Maybe now your code is failing. So in other words, you go back and forth, right? You don't have to write all your code first. You don't have to write all of your tests first. You can go, and you don't have to write them in parallel independently. You can go back and forth on these things. And that's what I generally do, right? I do write tests often, not always, but I go back and forth, right? Because if you subscribe to the pure test-driven development, that means that you're subscribing to a philosophy that your tests are always going to be correct. If you go with the other philosophical extreme, you're going with the assumption that your code is always going to be correct. Neither one of those assumptions is ever correct. It's always going to be somewhere in between. You can write good tests, you can write good code. Sometimes you'll write bad tests, sometimes you'll write bad code. So it needs to be a back and forth kind of situation for me, right? At least in practice. All right, let's come back over here and continue with the demonstration. Remember that we had 1, 2, 3 test cases here, right? Let's go ahead and compile everything together. Remember that you want to compile your library first, in this case, financialutils.c. Right? That produces a financeutils.o file that you can then bring together, financeutils.o, with your tests, financeutils.tests.c, and link in the math library here. Great. And when you run this, everything gets pass, 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 pass. Right? So far. Okay? Except that I'm a human here, and I don't want to sit there and go pass, pass, pass. Oh, that one failed. All right? In fact, how did it fail? Let's cause something to fail here. Let's go with a bad test case here, and I'm just going to remind myself that it should be 44 so I don't forget it. Okay? So I'll recompile this, and let's run it. Oh, it failed. Right? How did it fail? Is there any information there that will even tell me which test case failed or how to go about examining it? No. So the first thing I want to do is I want to make my failures a little bit more transparent, a little bit more verbose. So I'll say failed, right? On get monthly payment, on an input of %f, expected, I expected %f, but actually, but got, right? %f, and the line. And what I'll do is I'll print out the input, which is what? Oh, I don't have the input in a variable. So input, come back to that. I expected this, and here's the actual. There we go. So there are actually 3 numbers here. This value, and this value. So actually, let me just go ahead and hard code that, since it's a test case, on these 3 values there. There we go. So it's a 30-year mortgage here at 5 1/8% interest, and a really expensive $500,000 house, right? I just made those numbers up, by the way, right? I just button mashed, right? All right, let's go ahead and execute that. There we go. Now we've got some information that we can actually move on here. For these inputs, I expected 287743, and I got this value here. Now I know that my test case was wrong here, so I can go back and fix that, but at least I have some more information. Right? I'll probably want to go back, copy, paste this. There we go. Except that there's my input for that. That's a little bit better. Right? Copy, paste this, and fix this. Oops. Right? So copy, paste, copy, paste, copy, paste. Does anybody relish the idea of doing something like this? I don't like this. Right? Because I'm definitely going to be making a mistake here at some point, right? There we go. And probably not making a mistake here with just 4 things, but there we go. Now everything passes, but if it had failed, I would have actually some information to go on here, right? The other thing that we did on Friday, right before we left, was that we wanted a summary report. That I will keep track of the number of passed and the number of failed, and I will report it at the end. Printf, failed, %d, and then num failed. There we go. Passed. There we go. Num passed. Right? And then probably also a summary, right? Percentage. Right? %f. Right? How do I get a % sign? Can I just do 1% as the red indicates? No. But what do I need to do in C? 2 of them. That'll get my % sign there. All right, so the number passed divided by the total number, which is the number passed plus the num failed. Okay. Tell me, is that going to work? Integer divided by integer. What's going to happen there? In fact, it's telling me, warning, It expects a type double, but it is of type integer. So when I run this, I will get 0% passed. Oops, I should probably make it a little bit prettier there. There we go. There we go. And end line. So let's run that again. Failed, passed, percent is 0%. Even though I passed everything. Oh, what else did I forget? Because of my copy pasting habits. I'm not incrementing it there. I'm not incrementing it there. I'm not incrementing it there. Right? So you see that you get into this habit of copy pasting. What I'm doing here is informal unit testing. I'm writing my own boilerplate to do all this stuff, right? And I'm inevitably going to make a mistake. There. Now it's all mistakes are fixed except for this mistake right here. What is wrong? Integer divided by integer results in what? Integer division. Right? So one thing that I could do is I could typecast at least one of these things. Now I'm going to get 100% or 1%. What's the problem there? 0 to 1 needs to be scaled up to 0 to 100. So instead of typecasting, I'll go ahead and go with 100.0 times num passed. There we go. Now I get 100%. And if you want to, you can only two decimals is fine. Right? All right. Much better, because as a human, I just want to see 100% there. Right? If it's not 100%, then I'm going to have to go through with a fine-tooth comb and find out which ones failed. Right? But that's all I really want to see. Okay. All right. So lots of boilerplate, lots of copy-paste. That's not how you want to go in the end, right? So what we've been doing is informal testing, right? Formal unit testing, writing your own tests, and boilerplate reporting code, right? Even before that, though, we were doing something else. We were doing ad hoc testing, right? Testing as we went using manual input, output, right? So we need to graduate to yet another level, formal unit testing. You bring in a library to do all of the boilerplate stuff for you. In other words, all you should have to do is define the unit, the actual code, the input, the expected output, and it should take care of the rest. Right? Now, we're not going to cover it in depth here. In fact, we might not even cover it in depth. Instead, you'll, in lab in a couple of weeks, and in your hack in a couple of weeks, you'll look at it by example. But I do want to jump ahead here to take a look and see what it looks like. There are dozens and dozens of unit testing frameworks for any language. For C, the one that we're using in this class, and this is Lab 6 in a couple weeks here, is called CMACA. Why is it called CMACA? Well, C for C. MACA is short for mockery, and when you do testing, basically you want to generate a bunch of data, a bunch of fake data, a bunch of mock data, and that's where that's getting this name here. It used to be a Google library that they supported, and then they gave it up, or they abandoned it, and so it became free and open source, and now that we're using it. Right? It's pretty standard, though. And it looks something like this. So here is a test function. Instead of writing my own boilerplate, what I have is a bunch of input values, and then I call the function on those values. Right? Let's jump all the way down here to what it looks like in the main here. Right? So I'm defining a bunch of input and a bunch of expected output. And then once I've done that, I set it up with this CMACA unit test pre-state. I give it to this function, and it takes care of the rest. All I need to do in the end to actually run the tests is call this one function after you set everything up. It's like a big giant domino system, right? You've seen dominoes before, that you set it all up, and all you have to do, once they're nicely set up and everything, hopefully everything goes well, all you have to do is hit that first domino. They all fall and they all take care of themselves. Right? So the real work is in the setup. We've done that for you. Right? But you should understand that there are better ways of doing this. Rather than writing your own, in an informal manner, you should choose a formal unit testing framework and go with it. If you were in a programming language like Java, the de facto one would be JUnit. If you were in Python, there's a library built into the language called unit test, right? The same pattern over and over and over and over again in every single language, invariant. You've got this unit, you've got expected input, the actual output, and or the input, the expected output, and then it takes care of everything for you, right? And it generates a summary, okay? All right. Any questions on that so far? No? Okay. Then let's talk about some miscellaneous stuff. So, another advanced topic, right? Makefiles, or makefiles. There we go. It can be very complicated for larger projects. For larger projects, building all the code can be very complicated. Can get very complicated. You may have dozens of rules and dependencies, right? That one file depends on another, that depends on another, etc. There we go. Another language, a build system is necessary to keep things in order. We briefly talked about this on Friday, but when I was in industry, the last time I was in this industry, we had 100 programmers, and then 2 of them were completely dedicated. They were build engineers at the time. Nowadays, we call them DevOps, build engineers or DevOps, right? Development, operations. There we go. Right? Their entire job was not to write code, but to write code that compiled other code, right, and deployed that other code. This is also related to CI, which is continuous integration. Right? So if they've done their job and they've written all the scripts really well, and all the build scripts really well, and all the deployment scripts really well, they don't even have to hit a button anymore. Instead, every hour, it recompiles everything, deploys it. Recompiles everything and deploys it. Actually, it recompiles everything, runs through a bunch of tests to make sure that everything works, then it deploys it. If any test fails, stop, and somebody is alerted. Right? And the dream is to make sure that you do your job really well, so that you never have to do anything. Right? It's all completely 100% automated. Here's an example in that same project. It gets complicated enough, even with maybe a half dozen files here, that we have to give you a make file that looks something like this. Eventually, you'll be building this image driver program. The dependencies are right here. It depends on imageutils.o, an object file, colorutils.o, yet another object file. So we've got 2 different libraries here. And then this finally imagedriver.c, which has actually the main. Here's the rule for building it. We also have variables in this other language. Because if you want to change the compiler that you're using, do you change it here on line 11, 14, 17, 20, and 23? Nope. You change it on one line, and it's taken care of everywhere. Right? If you've got flag values here that you want to make sure that you're getting all the warnings, right? You make sure that you put that into a variable and then reuse that variable everywhere. So that if you ever want to shut off those warnings, you're only shutting them off in one place. The idea with a makefile is that it says, okay, you want to build the image driver? Great. It depends on these 3 things. Right? If this thing has not changed since last time you compiled, it's not going to waste time recompiling it. So it'll also take care of all that for you, right? That doesn't need to be recompiled. It hasn't changed since the last time we looked at it. All right? So it can take, sometimes really complex systems can take hours to build. Right? And if you can save on half hour, you do that because you want it to get built and deployed as soon as possible. In fact, there are old stories about how builds would take so long that they would make sure to do it overnight. That they would start the process so that the next day they could look at all the tests and then they'd have work for that day. Or, okay, well, I fixed something, now I need to recompile. So now I'm going to have to take the next 3 hours off because that's how long it takes, right? Nothing that you're going to do in this class is going to take that long, but there are systems out there that take forever to compile. Entire operating systems, for example. And if you can get away without having to do extra work, you do. The dependency rules here, like imageutils.o, there's another rule for how to build that. Right? So it goes out and builds this thing before it builds this thing. It takes care of all that for you. If you've got 50 different dependencies, and those dependencies have dependencies, and those dependencies have dependencies, and those dependencies have dependencies, right? You can see how it can get really, really complicated really, really quickly. Putting that in a makefile relieves you of the need of having to worry about that. Well, you have to worry about it once when you write the makefile, but at that point you're done. Right? So build systems are an important part of development as well, but we're not going to get into it too much. Right? The void keyword. So you can write functions that take no input. Right? You can write functions that give no output, right? So when they give no output, your return type is not an integer, it is of type void. Well, what is void? Void is nothing. It returns nothing. Let me come over here to my finance utils and just show you an example, right? I don't know. A prime example of this would be like printing a menu. Void print menu. Right, there we go. There. What values does it return? Nothing, because it's not computing anything. It's just simply printing out a menu to the standard output. And so the return value here is void. Are there any inputs to this function? No. You can also use the keyword void here. I would not recommend it. Right? It's extra unnecessary cruft. Remember cruft? Cruft Hall, you filled it up with garbage, and eventually, you know, nobody could do anything in it. No, throw your garbage away. This is not necessary. In fact, some bad things can happen with certain compilers with it, so just leave it. Right? So here's an example of a function that doesn't take anything and doesn't return anything. And you use the keyword void. Right? Example. There we go. All right. All right. So, oh, and then function overloading. Function overloading. Right? When you write a function and give it a name, foo, right? That is the only function that can ever have that name, right? Function names are unique, right? That's why we call them identifiers. It uniquely identifies that function. Consequently, you cannot have two functions with the same name foo. Should I go about and define my own function for sign and call it sin? No, that's going to conflict with the standard math library. Should I write my own function and call it printf? Probably not, because that's going to conflict with the input-output library. But what if I try to write my own function called getMonthlyPayment? But then I also want to bring in this third-party library, and it also has getMonthlyPayment. Now I've got a conflict here, right? That's called polluting the namespace. Writing functions pollutes, that's how you spell it, right? Pollutes the namespace, right? Once you write a function with a given name, you will conflict with any library you want to use that also defines a function with that name. Right? So, unfortunately, this is not this is a shortcoming of C. Right? Consequently, a lot of libraries will name their functions with a prefix. Right? For example, the we're not going to look at graphical user interface programming, but there's a graphical user interface programming library called GTK. GTK prepends all of their functions with GTK underscore, right? Plus the function name. Right? And doing that ensures that they're not going to conflict with any of your functions. So for example, if they wanted to create a function like GTK create menu. There we go. Not saying that that's an actual function in there, but there you go. That will not conflict with my function that I called create menu because they've got a GTK underscore in front of it. Right? The problem is, of course, if you want to bring in two libraries, both named GTK, right? Well, the likelihood of that is very, very low. Right? Some languages do allow you to define multiple functions with the same name, but possibly different parameters or inputs. Right? This is known as function overloading. Right? C does not support function overloading. Right? Consequently, how many absolute value functions do we have? We have abs that works on integers. What else do we have? Fabs that works on doubles. We also have labs that works on longs, labs that works on longs, and a couple of others. Right? In fact, there's a fabsfa, right, that works on just floating point numbers. We've only ever covered the first two here. Why? Because we only cover integers and doubles. Right? But there are a whole bunch of other ones. Why do we have a different name for the same concept for the same operation? It's because C does not support function overloading. Right? It's more of an object-oriented programming idea, and so C was born before the advent of object or the influence of object-oriented programming. So consequently, we don't have this in C. Right? You don't have this in a lot of languages actually. Even a modern programming language like Python does not support this. Because it's a dynamically typed language. Instead, it's got sort of function overloading in that parameters become optional and you have default values, if you know what I'm talking about, if you've ever seen any Python. But don't think of it as, oh, C doesn't have function overloading simply because it's old. Right? That's not true. There are plenty of modern programming languages that don't support function overloading as a design choice. Right? So keep that in mind. Once you have created a function, you have polluted the namespace. You can never use that function name on anything else ever again. So choose good function names. Right? All right. Any questions so far? Otherwise, the last thing I wanted to do today is ask you, how do functions actually work? Because this will actually lead into what we're going to cover starting next week on Monday. So what I want to do is I want to show this to you visually, right? So I've got a little program here. I've got a double n equals 10, double m equals 16. And what I'm going to do is I'm going to compute the average of those. What's the average of 10 and 16? 13, right? Right? So the way that I'm going to do that is, this is terrible code, by the way, right? Do not write a function that's sum of just two numbers. Just use plus, right? Do not write average of two numbers, right? Just use plus and divide by 2. Right? But I wanted to show this to you because it's a very simple concept that we all understand, but it illustrates how functions actually work. I've got over here what's called a program stack, okay? And I've got a stack frame. Everything here is relevant to the main function. Just look at the main. I've declared a variable n, there. I've declared a variable m, there. And I've declared a variable average. Right? Do those exist in the other functions? No, we've already seen that. But why? And the answer is, that's how functions work. Let me walk through this. Oops, get rid of that so I have some more room here. Let me walk through this. N gets assigned the value 10. M gets assigned a value 16. Right? What about the average? Well, what we're going to do is we're going to call that function. Right? Before we call that function, let's reason about this. Right? Are A and B the same thing as N and M? Well, they're the same value, but are those the same variables? No, because they're not even the same name. A and B exist over here in the average. Y exists in the average. So what we have to do is we have to create a new box over here in the stack. This is called a stack frame, and we will create yet another stack frame just for that function. Right? And I've got now average. A and B and Y exist in this stack frame. They only exist for this function. Over here in the stack frame that still exists for main, do you see A, B, Y? No. What about the values, 10 and 16, that get passed to this function? Let's watch that in action. When I jump into this function, it receives copies of those values, 10 and 16. I now have two sets of variables, each with the same value. So let's go ahead and go next. Well, guess what happens there? Another stack frame is created because I called yet another function, a, b, and x. Guess what? Those are not the same a and b. It receives the same values, 10 and 16, but those are not the same variables. I've got three sets of variables because I've got three stack frames here, okay? The way to visualize this is as a stack. In fact, that's why we call it a stack. So tell me, what is a stack? Just plain old English. Something on top of something on top of something, right? It's a pile of something. When you hear stack, though, you think very, very organized, right? The ideal here is of a stack is you go to the cafeteria, right? You've got plates, stacks of plates, right? What happens when you want a plate? Do you go down to the bottom of the stack and rip it out? What's going to happen to all the plates on top of it? It's going to collapse. And they're all plastic, I assume, right? Okay, so they're not going to break. All right, but when you clean a plate, where do you put it? Do you try to shove it in the middle of the stack? No, you put it back on the top. So the stack is growing up, or as you take things off the stack, it's growing down. These operations are called push on top of the stack or pop off the top of the stack. And for the very same reason that I gave you the analogy of the dishes over in the cafeteria. You don't actually have a stack of dishes and you're reaching all the way up here, do you? No, it's a spring-loaded mechanism. So if you've got a new dish, what do? You push it down, push the spring down so that you've got that dish on top of the stack. Now they're held in place by this little I don't know what you would call it, this little clip, right? And when you take it off, what happens? Well, listen very carefully to that clip. What happens? Pop, right? You're popping it off the top. Pushing things onto the top of the stack, popping them off the top of the stack. And that's how you should visualize this. When a program starts, the program code gets loaded up at the very bottom of the stack. Then you've got global variables, static content like miles per hour or miles per kilometer or something like that. Then the main function gets called. That creates a brand new stack frame that gets pushed onto the top of the stack. Main calls average. That creates a new stack and pushes it on the top. Average calls sum. That creates a new stack and pushes it onto the top. What happens when you return from these? And we haven't completed the simulation here. What happens when you return from this stuff? How do you know where to go back to where you came from? You've got a stack frame on the top. When you return, that gets popped off. Well, what's on the top of the stack now? When you return from sum, you're immediately back at the average. When you return from average, you're immediately back at the main. This is called a stack trace. You've got stack frame on top of stack frame on top of stack frame. So that when I start returning, guess what happens to that sum stack frame? It has a value of 26, 10 plus 16. That gets returned to the average stack frame. And it receives a value of y, is 13. Right? What happened to that frame? It got popped off the top and thrown away. It's gone. It no longer exists. Right? What happens when we return from the average? Same thing. We're back at the main. Now this visualization grew down, but I like this visualization a lot better because it is what it is, right? Now, does it matter with respect to a computer? Take your computer and turn it upside down. Is there an up-down with respect to memory? No. It's not physical. It's not like you're going to tip it over and then it falls or something because of gravity, right? Consequently, what happened to those those copies of A and B? Gone, right? Let's edit this code and try one more thing. So void swap int A, int B. There we go. So how do you swap two values? Let me go ahead and create a temporary value here and put A into it. Let me go ahead and put the value of B into A. And let me put the temporary value back into B. Right? Would you agree that that code right there would swap A and B? 10, 20 should be now 2010, right? Let's try it. I will create brand new variables here. 10, 20, and let's go ahead and call swap on A and B. Before that, let's go ahead and print them out. Print F, A, B are equal to %D, and the line, A and B. Right? There. Now, let's visualize this execution. I'm going to jump immediately to the end. And let's look at the output. Did it actually swap them? 1020, 1020. Why not? Was my code bad? I can guarantee you that this actually does swap A and B. Let's jump back to the first here and understand why. Int main, 10 and 20. I print them out, 10, 20 as expected. But when I call this function swap, guess what happens? A brand new stack frame receiving copies of the value A and B is created. Now watch lines 12 and 14. Guess what happened? A and B are swapped, 20 and 10. But are those A and B in the main? Nope, they're completely different variables. Right? And so consequently, when I return, that stack frame gets destroyed, and we're left with the original values. Right? So, can I write a function that actually successfully swaps? And the answer is yes, but I need something completely different than what we've been using up to this point. It's called pointers, and we'll start that on Monday. Otherwise, Wednesday, review. Friday, your actual exam. All right, good luck.